Okay, so welcome back to another video. So here we just want to show this little statement, and that's just to show that phi, aka the golden ratio number, is an irrational number. So there's actually many ways to prove this. I've seen one through math stack exchange that you can actually supposedly use, suppose that the golden ratio number is a rational number, and prove by contradiction by using the rational root test or root theorem. Another way I saw is you can actually use the recurrence relation that 1 over phi is equal to phi minus 1 and show with that whole contradiction that that indeed is a irrational number. But here I'm going to actually go with a little simple approach. And the approach of this format is, so I'll give it this way. The proof of this, the easier way to prove this, it's actually really, really short. So this format actually follows the same way if you were to show that the square root of 2 is, irrational. And here's a bit of a stipulation to see that we know that phi is equal to the following real number, 1 plus the square root of 5 divided by 2. So we can show that this is an irrational number. However, we're actually going to start a little bit smaller from a little result we'll do, and that is indeed we want to start off by showing this little lemma that the square root of 5 is an irrational number. So, and again, square root of 5 is that same format, just follows from the square root of 2 proof is irrational. So if you haven't checked out my square root of 2 is irrational proof, I'll leave that link in the description below. I also did a the Euler's constant E is also rational too, so I'll also leave that link down there as well. However, that proof does not follow the proof for E is irrational does not follow the same steps and format procedure that what we're going to do here for the square root of 2 as well. So other than that, let's actually just jump right in. So we're going to start with this lemma and say that square root of 5 is irrational. And so from here, what we're going to start off with this proof is that we want to suppose by contradiction that the square root of 5 is indeed a rational number. And so from the construction of a rational number, we say that for A and B, they're integers, B cannot equal 0, and also that the greatest common divisor, the GCD of A and B, is going to equal 1. So in other words, it's irreducible, it's co-prime. So then from here, we can actually use the definition and say that square root of 5 is equal to A divided by B. And if we were to solve this out, so I can just square both sides for 1, so it's A squared divided by B squared equals positive 5. And so if I just multiply the b squared to both sides, so it's a squared equals 5 times b squared. And so, as mentioned, this same proof is going to follow exactly just like we showed that the square root of 2 is irrational. So some notes we can make here / observation is that we see that a is divisible by 5. I'm just going to abbreviate this and say div for divisible, is divisible by 5. And so what this means is we can actually write a little new equation saying that a is equal to a multiple of 5. So that means a is equal to 5 times c. And so from here now, what we can do here is I'll just actually plug this back in to the a squared equals 5 times b squared. And so we can actually make a little more observations. So 5 times c and square equals 5b squared. That says that this is equal to 25c squared equals 5b squared. I just divide 5 to both sides, so I have 5c squared is equal to b squared. And so another observation, this actually follows the same thing, just like before we showed that a is divisible by 5, we can also see that b is also divisible by 5. And so that actually forms a little contradiction because we said that by construction of rational numbers, the GCD of A and B is equal to 1. However, we just showed that A and B, they have a common factor of 5. So that means every time it's always going to be reducible. That actually, contradicts this definition. So let me actually write this out. So if we said that A over B is rational, then that would have to mean that both the numerator, so I'm just saying NUM, just abbreviate, and then the denominator DEM have a common factor. Let me put this in the next line. Have a common factor of 5. And so that ignores the definition that this is the irreducibility. So it's reducible over here. And so that actually has to say that that contradicts, the definition of a rational number. And so that has to imply that now that square root of 5 is indeed irrational. And just like that, we actually just proven our little lemma. And so this is nice. That can actually help with the result, further justify the results from what we're given. So let me actually just box this over here just to say we're completed over here with this lemma. And so now we can actually go on to the main statement that we want to prove. And now, so this follows the same thing again. So proof, I'll just say for a given, which is, you know, what we want to show this whole time. Then we say that suppose by contradiction that 1 plus, I'm just gonna write this out, 1 plus the square root of 5 divided by 2 is rational. And I'm not gonna write the same thing again for the little pieces, what defines a rational number, but it actually follows the same. So for A and B are integers, B cannot equal 0, and then the greatest common divisor of A and B, they have to equal 1, irreducible or co-prime, whatever you wanna put in that definition. So that follows for this statement over here. And so what we can do now is then we can write this as A over B is equal to 1 plus the square root of 5 and then divided by 2. Solve this out, what I can do is I'll just multiply a 2 to both sides, and then I'll subtract 1 from over here. That says that now we have 2 times A and then divided by B. Subtract 1 has to equal the square root of 5. So what does this imply? I'm going to save all that writing and just go straight for all the explanation. Since we said that by definition that A and B is rational, then this has to mean that 2A divided by B minus 1 also has to be a rational number from, you know, that construction as well. You can see that whatever numbers you plug in, you'll always get a rational number for here, which further implies that square root of 5 has to be a rational number as well. But this is weird because we have run into a contradiction from that lemma, and we just showed that the lemma that the square root of 5 is irrational. So again, contradiction. That's implied that now the golden ratio number 5 is actually going to have to be an irrational number. And so just like that, we have proven our given statement that we want to show. Simple as that. And if there are any other ways that we can show that the golden ratio number is irrational, you know, feel free to post that in the comments below. Again, I saw the ones that from math stack exchange from those methods that I've seen. So if there's any other ways you can show, then, you know, feel free to put that down. So yeah, that's pretty cool if you ask me.